Hi students, welcome to the chemistry classes. So I hope everybody is doing good. Now what we were on to? We were on to the discussion of nucleophilic substitution reactions, right? So we were discussing about nucleophilic substitution reactions and that too, two types of reactions. I hope everybody remembers that we discussed about SN1 and SN2 mechanisms, right? And these mechanisms hold a great importance as respect to your exams point of view, right? Now, I was discussing about the stability order of the carbocations, different type of carbocations in the last session, right? So what were those? We had discussed the simple carbocations, that is the tertiary, secondary and primary, along with some of the resonance stabilized carbocations as well. So those examples are very, very important. I hope everybody has understood those because we'll be having different resonance structures in those carbocations and those will be deciding the stability of that particular carbocation, right? So what was the order? The order was benzylic, right? Benzylic, what I am talking about? Benzylic carbocation, right? Now the next was allylic carbocation. Fine. So how does the benzylic looks like? So the benzylic looks like you have to draw first the benzyl, right? That is the benzyl, and what you need to do is make it a carbocation. Fine. A positive over here. And how does the allylic look like? Allylic will be having the allyl group along with that positive charge. So it will be having something like this. Okay, it should be CH2 over here. Right? So that was allylic. Now, as I told you, why benzylic is more stable than allylic? Because it has got more resonance stabilization. It has got so many structures, whereas allylic has got only two resonance structures, two possible Lewis dot structures possible. Now, I'll be placing the simple carbocations as well. Where will those be placed? They'll be placed right here. Clear? So as I told you, the resonance stabilized carbocations will be having more stability as compared to my normal ones. Okay? So these are resonance stabilized. Fine? So since these are resonance stabilized, placed earlier, and these are the normal ones. Now, what about the question that I asked you in the last session? That was something related to the aryl carbocation. Now, what will be the aryl carbocation look like first of all? So, this is the benzene, this is the aryl group, right? Yl means one vacant position. In that vacant position, I am not placing anything, but I am placing is a positive charge. Fine? So this particular positive charge will result into what? I need to decide the stability of this aryl carbocation. So I hope everybody has tried this question, quite an important one as well. So this particular question actually tests your knowledge, whether how much you know about organic chemistry, how much you know about the basic criteria for organic or not, right? So this particular aryl carbocation. Now, what will happen? Where this will be placed in this particular series? That is the question. So, as a matter of fact, I would like to tell you the answer for this particular question. The answer to this question is that the aryl carbocation is the least stable one. Very, very unstable. So, since the aromaticity over here, if you observe, it has got the aromaticity, it has been disturbed. Aromaticity, Ti, right? Aromaticity of the ring is disturbed over here, right? due to which what has happened? Due to the disturbance of this aromaticity, because of this positive charge, this aryl carbocation is very unstable. So that is very unstable. Why so? Why I am saying that the aromaticity of this particular ring is disturbed? So since you must be knowing what Huckle Rule is, right? Huckle Rule says for a compound to be perfectly aromatic, to be perfectly stable, I need to have a planar structure. But due to this positive charge over here, the carbon is not acting, is not behaving as planar, right? So due to the disturbance in the planarity, the ring gets distorted somehow. Some of you might be having a confusion. You might be saying that this positive charge will easily be diminished or stabilized by these pi electrons, but this is not so, right? There will be no positive charge stabilization from this particular ring, but what is happening is the aromaticity is getting disturbed in fact. So due to that, making it very, very unstable carbocation, in fact so unstable that I am going to put this particular aryl carbocation at the very last of the series. Fine. So here will be the aryl carbocation placed, right? So here the aryl carbocation will be at the very last, right? I hope everybody has got it by now. So that completes our SN1 and SN2 mechanism fully, right? So I hope everybody has revised those, because now it's the test for your knowledge. I'll be giving up 2 or 3 questions related to SN1 and SN2 mechanism. You need to judge that which compound will be giving SN1, which is giving SN2, or the order of that, right? So first and foremost question, number 1. So I've been given 2 compounds. First you need to decode the compound. There has been the entire bond line formula. You need to convert this. Either some of you, what you can do is, if you are having a difficulty in judging that what and how many carbons are there, possibly there over here. So what you can do is, you can decode it and convert it into a structural formula, proper structural formula. Or what you can do, some of you that have enough practice of it can just straight away answer the question, right? So I've got 2 compounds. I need to tell that which of them will be giving SN2, right? So I need to find out the order of SN2 reaction, right? So the first question arises is, how did I judge that these 2 particular compounds will be giving SN2? First is that particular question. So you must be having an idea about SN2. In SN2, what is the order of the type of alkyl halides that have been taken? So that is, primary must be having the highest rate, because it will be having the least possible hindrance, right? Followed by the secondary and the tertiary. So due to that, I infer that these 2 are nothing but having the primary carbons. I am talking about this particular carbon which is directly attached with the halogen. Why I am talking about only and only this particular carbon? Because I am considering CX bond, right? My main concern is nothing but the CX bond, which will be once cleaved, right? Which will be then cleaved during the reaction, right? So that is how I can find out that these are nothing but primary carbons, and they will be showing most probably SN2, right? Now what you need to find out is, out of the 2 which will be giving SN2 very fast. So what should be the approach? As I told you, the approach should be finding out the type of carbons, right, in SN1 as well as in SN2. But now both the type of carbons are same. So what was the first approach? Type of carbon, which is same, right? Same in both of them. So I rule out the possibility for this particular criteria, right? Now the next, what can I say? I have not been given any kind of information about the nucleophile. So I cannot judge that which nucleophile, is it a strong that they have taken or is it a weak one? I don't know, right? So that particular criteria can also not be fulfilled. Something about the solvent, again the information is not given. So what is the information? What is the difference you can see very well, which is very well visible in between the two molecules? That is none other than the type of halide. Right? So what you need to choose is type of halide, is it? What does the type of halide, what kind of information will it give? Is it not something related to the leaving group? Yes, that's right. So what we need to do is, since these two halides, after the happening of this SN2 reaction, they will leave at some point of time. So I need to decide which one is the better leaving group, and then I'll be confirming that out of the two, which will be giving higher rate of SN2. Fine. So is this order of SN2 reaction? I can say the reactivity order, right? Not that order. I'm not talking about this particular order too, right? So out of the two type of halide, that means I'm confirming the information about the leaving group, right? Halide, nothing but considered as a leaving group. So which is the better leaving group out of the two? So the better the leaving group, faster the SN2 reaction, is it? Yes. So faster the SN2 reaction. Out of the two, as I told you, bigger the size, better it will be able to hold on the negative charge onto it and disperse, right? So that will be the better leaving group, and that will give us fast SN2 reaction, right? So out of the two, which is bigger? Iodine is definitely bigger, is down the group, right? So what will happen? It will leave the vicinity very quickly and it will give the product, the desired product very quickly, performing the SN2 faster. So if I say about the reactivity order, which is more reactive out of the two? Definitely this particular product. And what is the name of this particular product? 1, 2, 3, 4. 4 carbon atoms attached with iodine. It's butyl iodide. Fine, that is the name. Everybody gets that. So it's not such rocket science after all. Now, let's move on to the very next question if you are done with it. So the second one, I say that I have got one possibility, CH2Cl, right? Is this a benzyl? What is this compound? This is not benzyl. If you have been mistaken, observe there is no such kind of an aromaticity, it's just an aliphatic ring. Fine. So do not get confused via that. So if you are confused, you may think of the benzyl carbocation later on. So always and always try to observe what all molecules are given very carefully. Fine. First, the second one, fine, and the very third. Now you can see the difference between the three compounds. What do I need to observe over here? I need to find out again the reactivity order, which of the molecules will be having the highest reactivity order towards SN1 mechanism. This time I am talking about. So this is order of reactivity towards SN1, right? What will be the order? 1, 2, 3. I'll be naming it as A, B and C. First and foremost thing, what do you need to look at? You need to look at the type of carbocation that is formed, right? As I told you, I need to observe the type of carbon. In SN1, we observe not the type of carbon, but a better version of it, the carbocation, right? So I need to observe is, let me just write it over here, type of carbocation formed, right? Now what will be the approach to find out the type of carbocation over here? Because over here you need not go into the detail of having the entire mechanism, writing the entire mechanism. What you just need to do is, how is the carbocation formed? The carbocation is formed when this Cl will go off, this halide will get removed, and that is how the carbocation will be generated. So where the positive charge will be coming up? So that is how you need to do. Positive charge here, next positive charge here, fine, and the third, I remove this and the positive charge comes up here, fine. So now I have got 3 carbocations generated. What is the order of reactivity of the carbocations? That will give our answer. So over here in the first very question, what do you see? You see what type of carbocation? Is it primary, secondary or tertiary, or the resonance stabilized? So it could be any one of those. So you observe something that this particular carbon is attached with only one carbon right here. That is why I am making it as primary carbocation. Fine or not? It's very easy. Now this carbon over here, which is having the positive charge, is attached with 1 and 2 carbons. That means this is secondary carbocation. What I am left with is, can you see an aromatic ring over here? So this is none other than what? We have just discussed about it. So that is benzylic carbocation. Fine. So that is what we have generated over here. So this is the benzylic carbocation that we have got. So what will be the order? Since I told you the benzylic carbocation is resonance stabilized, right? So I will be just writing benzylic over here. So this is resonance stabilized. This will be having the highest reactivity, and then there will be secondary, fine, and then it will be primary. That is how we have written the order. That is the benzylic, the resonance stabilized comes first, followed by allylic. We are not concerned with allylic because it's not given in the question. Tertiary, secondary, primary. So that is how it's going, and there is no such aryl carbocation over here. Fine. So what will it be? The order will be C, B, A. Fine. I hope everybody has got the right order. That is C, B, A. Fine. So that is the answer to the question. Also, if I add up something over here, the D option. So I'll be writing down the D over here. That is D. So what can you find out? Can you now arrange all of those? We have discussed about all the 3. I hope you have understood. Now something about this particular. What you need to do is, first you need to generate the carbocation and see what type of carbocation it is, right? So I'll be generating it. Fine. The halide is removed, positive comes over here. The option is none other than what I had explained earlier, that is aryl carbocation. Fine. So it is none other than the aryl carbocation which is formed over here. Fine. So this is a very unstable, we already know, right? So this is very, very unstable, thereby making it even not in between something A and B, but even more and more unstable than the normal carbocations as well. Fine, the aliphatic carbocations. That means this will be the least possible option, the least stable option. Fine. So that is the entire process, how we are going to check whether a compound is feasible for SN1 or SN2, right? So what you need to do, if I ask you something about that, will this carbocation, will this alkyl halide is able to perform SN1 or SN2, so what do you need to answer in that particular thing? So let me just give you an example for that. If I ask something related to a compound, right? There is a compound, fine. This is tertiary butyl chloride. Clear? Now I ask a question that which will be the possibility? Will it be performing SN1 or SN2? So question is, will it perform SN1 or SN2? What could be the possible option? What could be the possible answer? So the possible answer over here will be when I consider the type of compounds, right? So the type of compound which you can see, the type of carbon over here which you can see is, this is tertiary carbon, right? So if I try to perform SN2, that means I need to attack the nucleophile from the back side, right? So here is the nucleophile coming on. What does the nucleophile observe? It observes a lot of steric hindrances, thereby making it very less possibility, right? Very less. In fact, I can say a negligible possibility for this molecule to perform SN2 because it is not letting the nucleophile in. So the nucleophile cannot have the backside attack at all. Now what will it prefer is, the formation of carbocation is the second preference of it. So it can easily go off, form a very stable carbocation. So it's stable carbocation formed, thereby creating the possibility of SN1 specifically. Clear? So that is how you need to judge. Fine? Now comes up the real thing, right? We have discussed the entire mechanisms of SN1 and SN2. What we have to discuss now is the nucleophilic substitution reaction and its main thing, the stereochemistry. How can we observe these reactions in particularly 3D? By this time, we have been doing all the reactions on the board on just a single plane. But we haven't discussed, we haven't seen the stereochemical aspect, the stereochemistry of all those particular, all these molecules which are involved in the reactions. Now, what about stereochemistry? We already have read something about stereochemistry. Fine. What is basically stereochemistry? It is nothing other than the spatial arrangement of molecule in 3D space, right? Now what is the spatial arrangement? If I talk about, let us just say that this particular, there is some molecule, fine. I write this is a carbon and these are 4 hydrogens arranged somehow, fine. But what about when I talk about all of these bonds to be seen like this, somewhat like this, right? I can have a 3D arrangement of these bonds as well. I am not saying that all the bonds are completely in the plane of paper, but they could be, because all the things which we are discussing are real, are existing around us, and nothing is in 2D, but what we all see is all of them is in 3D, right, like this ways. So it could be any possible arrangement, and that possible arrangement is known as the spatial arrangement. That means the arrangement of the molecules, the arrangement of all the atoms present in 3D space, right? So that is how we consider the stereochemistry. That means the stereochemical aspect. What is the stereochemical aspect? That is, whenever we are seeing all the reactions getting performed in 3D, all the molecules are rotating and I can see all the bonds properly, which all bond is breaking, which all bond is making. So that is what we see in stereochemistry. Fine. So in that particular aspect, why we have joined the word nucleophilic substitution over here? That is the point now. Definitely we are considering each and every reaction in 3D. But let me just give you an idea that why we are actually concerned about the stereochemical aspect, specifically in nucleophilic substitution. So if you see over here, in SN1, fine. So what we have done in SN1, let me just write it over here itself. There was the formation of a carbocation, remember? And that carbocation, this particular carbocation was trigonal planar. That means having a plane. It was present in a single plane, right? So if I talk about a single plane, something like this. Wait for a moment. Right. So if I say that this is nothing but, that is how the molecule will be arranged in a single plane. Fine. Now, that was the trigonal planar geometry that we have done. Now, was the final step? The final step which is related to the nucleophilic attack. So, the nucleophile can attack from this ways, right? And the nucleophile can attack from this ways. There are two possibilities. In each of the possibility, I'll be getting different arrangements of atoms, right? So there are two possibilities, two possible arrangements. And you know what? The two possible arrangements, these two possible arrangements is known as nothing but the process of racemization, right? So a new term has come up over here. That is racemization. Fine. Racemization or the mixture. There could be a possibility that the mixture of two will be formed. That means a product from this side, a product from the other side. So it could be the racemic mixture. Fine. So these are the two possibilities. Clear? And now, what is basically racemization is and what is basically the racemic mixture is? The answer to this question will be given by the stereochemistry, the stereochemical aspect of the nucleophilic substitution, right? Also, what I would like to tell you over here is, in SN2, remember, we get an inverted configuration. Fine. So that means this inverted configuration also you must be having a confusion that what is this term configuration used over here? Why is this inverted and why cannot I say that this is just one and the same thing? One and the same compound only. If this is inverted, it opens like this, right? And earlier it was like this. Remember that we have already discussed. So basically you can say that both the compounds are nothing but the same. If I look from this side, it will look same. But that is not the reality. The compounds are not same. The arrangements will be different and the views could change, but the compounds are completely different. Why they are different? So again, the answer will be given by nothing but the stereochemistry. Fine. So what we will be discussing in the next session is a detail about this particular stereochemical aspect, something new to you and quite an interesting one. Have a very good day.